Today we're going to talk about polynomial functions. We're going to cover the most common polynomial functions, what makes up a polynomial, and the end behavior in graphing. Recall that a monomial is a number, a variable, or the product of a number and one or more variables with whole number exponents. A polynomial is a monomial or a sum of monomials. Here are some examples of monomials: binomials and trinomials. A polynomial function is a function of the form f of x equals a subscript n x to the power of n plus a subscript n minus 1 times x to the power of n minus 1 plus ... which could include as many terms as the polynomial has, plus a subscript 1 times x plus a subscript 0. Where a subscript n is not equal to 0, the exponents are all whole numbers and the coefficients are all real numbers. For this function, a sub n is the leading coefficient, n is the degree, and a sub 0 is the constant term. A polynomial function is in standard form when its terms are written in descending order of the exponents from left to right. The examples above are written in standard form. As you can see, the highest exponent of 2 is first, the next exponent of 1 is next, and then 6 with no x. Degree is the greatest exponent. So when the degree is 0, we have a constant function in the form f of x is equal to some number. When the degree is equal to 1, we have a linear function. A polynomial with degree 2 is called a quadratic. A polynomial with degree 3 is called a cubic. And when the degree is 4, your polynomial is a quartic function. Subscript is used in math as a label. Notice that the subscript number for each coefficient matches the exponent of the variable. So if you were given a quartic function and I asked for a subscript 2, I would be asking for the coefficient of the x squared term. A function is not a polynomial when it has an x under a root, an x with a negative power, an x in the denominator, an x in the exponent, or an x with a fractional exponent. Decide whether each function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. The function in part A is a polynomial. To write it in standard form, we need the exponents to be in descending order. That is already the case. The first exponent is 3, the next exponent is 1, and of course the constant is at the end. Because it's in standard form, we'll get all this information from the first term. The degree is n, your highest exponent, which is 3. If n is 3, we have a cubic function, and the leading coefficient is the number being multiplied by the x with the highest exponent. What about the polynomial in part B? I see a root, which I'm not allowed to have on an x, but I can have a root of a number just as long as the coefficients of the polynomial are real numbers. Root 2 is a real number. Even though it's irrational, it's not imaginary. But if you notice, our exponents are not in descending order, so go ahead and rearrange g of x to write it in standard form. The degree of this polynomial is 4, making it a quartic, and the leading coefficient is root 2. Part C is not a polynomial because you have an x to a negative exponent. And part D is also not a polynomial because x is in the exponent. Polynomial functions have a pattern for their end behavior depending on whether the degree of this function is odd or even, and whether the leading coefficient is positive or negative. End behavior is literally the behavior at the end of the function. This function could have no additional waves, or it could have large waves in between its end behavior. That is why this portion is dashed in between, because we don't know how many turning points we have in between, but it doesn't matter because this is helping us with the end behavior. What's happening as x's are approaching infinity all the way to the right, and what's happening as the x's are approaching negative infinity all the way to the left. This graph represents a function with an odd degree. One side goes up, one side goes down. I always remember x cubed, and x cubed has a positive coefficient of 1. So when my leading coefficient is positive, all the way to the left, the y's are going down, all the way to the right, the y's are going up. Now, how do we write that mathematically? End behavior describes what the y's are approaching when you look all the way to the left or all the way to the right. When we look all the way to the left, these y values are decreasing or approaching negative infinity. So we'll write that as f of x, or the y's, approach negative infinity as the x's go all the way to the left, or as the x's approach negative infinity. The y values are increasing or approaching positive infinity as the x's go further to the right, or as the x's approach positive infinity. Our second graph is just a reflection of the previous graph, meaning my leading coefficient is now negative. When that happens, our end behavior has been reflected. So now, as x's are approaching all the way to the left, your y values are approaching positive infinity, and your y values are approaching negative infinity all the way to the right. When the end behavior of a polynomial function is the same, that means our degree is even. When both sides approach positive infinity, you have a positive leading coefficient. And when both sides approach negative infinity, you have a negative leading coefficient. Remember, this is the same for all end behavior statements. We're asking, what do the y's do as the x's go to the left? What do the y's do as the x's go to the right? When the degree is even and the leading coefficient is positive, the f of x or y values approach positive infinity. And when the degree is even but the leading coefficient is negative, f of x will approach negative infinity on both sides. Remember, end behavior doesn't tell us how many turning points or how many waves there are in between, but it does help us with what the y's will eventually be approaching all the way to the right or all the way to the left. Now that you've learned the leading coefficient test, or the pattern of end behavior for polynomial functions, part B isn't written in standard form. The highest exponent, or the degree, is actually 3. And here's our end behavior. For number 3, we're going to find the intercepts, end behavior, and graph the function. To find the x-intercepts, we make y equal to 0. Can we solve this by factoring? Actually, yes, you may remember factor by grouping from Algebra 1. To begin, you group the first two terms. What is the GCF of the first two terms? Because we start with a negative, we need to make that part of our GCF. Negative x squared goes into both of these terms. Now divide each of these by negative x squared, and you get x minus 1. Now take out the GCF from the next two terms. That would be 3 and positive 3. X minus 1. And what do you know? I have two terms, a product here and a product there. And both of these products have a common factor, x minus 1. So I'm going to factor out the common factor, meaning I'll write it one time, and then I'll divide each of these terms by that factor of x minus 1. Our second factor will be negative x squared plus 3. Now we can use the zero product property to find the x-intercepts. To find the y-intercept, I need x to be 0. And then I also need to know the end behavior. My degree is 3, which is odd, and my leading coefficient is negative 1. I know that means I'm going to go up this way and down this way. Let's graph our intercepts and see if we need to plug in any more x values in between. going to plug in an x value in between the intercepts, 1 and 1.7. So I'll plug in 1.5. Now I believe I have enough points to graph. This is an x cubed function reflected over the x-axis. So the options it could be would be this, where it's consistently decreasing the whole time, or something like this, where it has 2 waves. It could never have more than 2 waves, or what are technically called turning points, because the degree is 3. So if the degree is 3, it cannot have more than 2 turning points. If the degree was 4, it could not have more than 3 turning points. The maximum amount of turning points is 1 less than the degree of the polynomial. And this is just a sketch, so it's not going to be perfect. This x-intercept, I'm going to approach negative infinity forever and ever and ever. Okay, actually, I think I'm going to plug in -1 because I'm not really sure that our y-intercept is also our turning point. So when I plugged in -1, I got -6. That still may not be our actual turning point, but it's a lot closer than -3 was, right? So now we're going to come back up through this x-intercept, and what happens after that? Oh, we keep going toward infinity forever and ever. You should be familiar with basic characteristics of polynomial function graphs, but we're not going to spend an extended amount of time graphing them until we get to calculus, where we have tools that make graphing polynomial functions exceptionally easier. Polynomial functions can also have some symmetry. They could have y-axis symmetry, like your parent graph of x squared and x to the 4th, or they could have origin symmetry, like your parent graph for x to the 3rd. A function f is an even function when f of -x is equal to f of x for all x in its domain, and the graph of an even function is symmetric about the y-axis. A function f is an odd function when f of -x is equal to -f of x for all x in its domain. The graph of an even function is symmetric about the origin, meaning if you rotated the graph 180 degrees about the origin, the result would be the original graph. The graphs would overlap perfectly. So what do you need to do to determine if a function is even or odd? And keep in mind, a lot of functions are neither. We need to plug in -x instead of all the x's. A negative to an odd power stays negative, so -x cubed plus 7x. This is almost the same function, except the sign for both terms has been switched. Or could I even write it as the entire function has now been made negative? If that's the case, then we have an odd function with origin symmetry. Plug in -x. Notice your degree is even, so the only possibility you have for this function is that it would be an even function or neither. When a negative is to an even power, it becomes positive. So this function has remained unchanged even when you plugged in -x into all your inputs. That means this is an even function, and that would mean it has y-axis symmetry. Try part C. Notice that only one of your signs has changed, so this is neither even nor odd. And there's our overview of polynomial functions starting Unit 4.